Blah, 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 blah. Blah, blah. Ah! Okay, it's recording as we speak, so we are ready to go. So we are talking about chapter number 3 mostly. Chapter 3 is about two-dimensional motion, projectile motion essentially. So the content is very similar to what we've already studied in chapter 2. The only thing that's kind of being added is the fact that we've got 2 dimensions to work with. And so, obviously space is 3-dimensional, but the truth of the matter is once we get 2 dimensions, the 3rd dimension is pretty straightforward generalization. And the truth is that even in the book we don't really deal with 3-dimensional motion. The only real exception to that is when we deal with magnetism, but that's all the way in 203, so we don't have to worry about it for now. So in terms of 2-dimensional motion, we will still be talking about accelerated motion. Primarily we're still talking about motion in free fall because a projectile is under the influence of gravity. So gravity exhibits constant acceleration on the object that's moving. And so really what we're adding is a lateral motion on top of it. And that's kind of the whole thing that happens in chapter 3. All right? So so the main thing I guess I want to just start off the discussion with is that we talked about the fact that acceleration is defined as any kind of change in velocity, but velocity includes both speed and direction, right? So technically acceleration involves any change in either speed or direction. And so last time we talked about acceleration that is parallel with the velocity. So if we're talking about an object that's moving at a certain speed in a certain direction, what we talked about is acceleration that is either in the same direction or opposed to the motion, because we were only dealing with one-dimensional motion. And so by kind of constraint, the arrow associated with the acceleration is always aligned with the velocity. So now what we're doing is basically generalizing this situation and saying, okay, well, what if the acceleration is not pointing in the same direction, but maybe in a different direction? For example, what if it's pointing perpendicular to the velocity? What happens, right? And I think you can just feel what's going to happen, right? If it's moving in this direction and I accelerate it, if I change its speed, or if I change its velocity, essentially if I kick it, right? If I kick it, it's going to bend up, right? It's going to move in that direction. And that's kind of the shortcut paper on acceleration that's perpendicular to the motion, is that acceleration that's perpendicular will deflect the motion of the object, right? So acceleration that is parallel will change speed. Acceleration that is perpendicular changes direction. Okay? So this is kind of the 2 components of velocity, speed, and direction, and acceleration can affect either one. Now, the other thing that we're mixing into this chapter, so I deliberately skipped chapter 1 in order to kind of move into chapter 2, because chapter 2, I think, has 2 advantages to it. One is we start talking about acceleration from the get-go, and acceleration is probably one of the primary quantities that we deal with, so getting it introduced early the better, I think. But also, we had a really set way of solving all the problems, right? idea was, okay, collect all your data, find 4 variables, that kind of step-by-step approach to solving the homework problems. We won't always have that advantage. We'll have to be a little bit more creative in future chapters. But one of the advantages in chapter 2 was there was one simple, straightforward algorithm for solving the problems. In this chapter, we'll be able to leverage that, but things get a little bit more complicated because we have to layer into the whole analysis this directionality. And the directionality is kind of what chapter 1 is about when we talk about vectors. It's the whole point of vector math, is to deal with this directionality and how do we so we've got these 2 special cases, but what happens if the acceleration is at an angle like this? Well, the truth is it's going to do both of these things, right? It's going to both change the speed and change the direction. And part of the way of thinking about that is, well, the acceleration's got a component that's parallel and a component that's perpendicular. Part of it is pushing in the direction of the motion, which changes the speed. Part of it is moving perpendicular to the motion, which is changing its direction. And it's that part of, how do we know how much of this is parallel, how much is perpendicular? That's what vectors are all about. Okay? And that really, for us, is always going to come down to trigonometry. Okay? And so, this next slide here begins to basically summarize the most important parts from chapter 1 in terms of vectors and trig. Okay? Everything comes down to this right triangle. Okay? And basically, if I've got a quantity of v, right? Pretend this is velocity, for example. Velocity has both magnitude and direction, so I can represent that on the board with an arrow. The arrow has both a magnitude, its length, its size, and a direction. Depends on how I orient it. Also, you know, this arrow is different than this arrow, right? So that's why I draw the arrowhead, because these 2 vectors are potentially different. So, you know, on the board I can draw this vector, but how do I deal with it analytically? And the way I deal with it analytically is through this idea of components. Okay. So I say this vector, this arbitrary vector that's pointing in an arbitrary direction, has an x and a y component. And it all comes down to basically the direction it's pointing relative to the coordinate system I have in place. So in this example here, the implied coordinate system looks like this. This is my x, and this is my y. All right, I've got an x direction, and I've got a y direction. Okay. And so you just kind of imagine you've got a piece of graph paper that's overlaid on top of the problem. And that graph paper is essentially the coordinate system. The x component of this black vector here, the x component is nothing more than the horizontal distance on this triangle. Right? So I label this v sub x. So it's the x component of the vector v. And this distance here, I call the y component of vector v. Okay? And once I draw that out and kind of make those definitions, now you can start to see why trig is going to come into play, because those lengths are all related through the trig functions, right? So the sine of this angle, theta, sine is opposite over hypotenuse, right? The opposite in this case is opposite to this angle. This length here, yes, vy. Vy. The hypotenuse of this triangle is the length of this vector. And the symbol for that is v. Now there's just a little bit, it's almost not even worth mentioning, but there's a subtle distinction between what I've drawn here, or what I've written here, and what I've written here. When I write v with the little arrow in front, that's supposed to indicate that I'm talking about a vector. When I leave off the little arrow on the top, I'm talking about just the magnitude of that vector. Okay, so if I'm being very careful about what I'm writing on the board, that indicates a vector, but the magnitude of that vector is symbolized with just the letter itself. Okay, so that's kind of the difference here. So when I write this, I'm careful. The hypotenuse is not the vector. The hypotenuse is the length of the vector, right? Nonetheless, that formula is straightforward. Cosine is Vx now, because this is the adjacent side, this is the hypotenuse. The tangent is opposite over adjacent, Vy over Vx. Now, for us, it'll be a little bit more convenient to rewrite these just by cross-multiplying as Vy equals V cosine sine. Those two there in particular. So these two formula, are how to go from knowledge about the vector. So if I have a vector and I know its length and its orientation, right, its angle, this is how I figure out what the components of that vector are. Right? So as I see in the slide, if you've got the vector quantities and you want to figure out the components, use these formula. What happens if you want to go the other direction? What if I've got Vx, Vy, but I need to figure out the magnitude and the direction of the vector, right? Well, in that case, I'm going to use this formula here. This formula here allows me, basically, if I take the inverse tangent, both sides, I get the angle here is the inverse tangent of Vy over Vx. See the advantage here on the right side, I've got nothing but components. I've got the Vx and the Vy, so this allows me to go from components to the vector. And the last thing is the magnitude of the vector, and the magnitude is just Pythagorean's theorem, right? So the magnitude is given by that. So these four equations are really the main thing that you need to understand when it comes to vectors, because every time we deal with any kind of vector quantity, one of the first things we're going to do is take that vector and split it into its components. And the reason we want to do that is because once we have it split into its components, we can kind of forget about the directionality. Now we're just dealing with one dimension, and then that one dimension, then we just fall back on the techniques we used in the last lecture. We used in lecture 2. So that's kind of the trick that we're doing. So I think that's actually, 2 slides. So this slide here, the diagram, basically, so one thing that is a vector is displacement. Displacement is basically, if I start here and I end here, what's the difference between those positions? That's what displacement is. So if I move along this vector A, and then I move along vector B, basically pretend this is a little map that I'm walking back and forth on. I can consider the combination of those two as being kind of just the same as going from A to C. Right? This is A, B, C, and I go from A to C. That's really the same net displacement. If I forget about the fact that about the position in between. So, frequently what we'll be wanting to do is to combine these vectors. What's the combined impact of vector 1 and vector 2? And the way we symbolize that is by saying that we're adding the two vectors together. I say that vector C is A plus B. I'm making it sound simpler than it really is. that equation vector C equals vector A equals vector B. That equation looks like it's just simple algebra because it's using symbols I'm familiar with, right? But these vectors have got directionality associated with them. So if I think about this as vector A is maybe 30 meters north, and vector B is 40 meters east, then what is C? I'll tell you one thing, it's not 70 something. Because 30 meters north represents an arrow that looks like this. 40 meters east represents an arrow that looks like this. The combination of those two is not going to be 70. Right? In fact, the way I do this, kind of mentally, you imagine taking this vector and putting it kind of tail to tail, put the tails together. Or, it's equivalent to putting a tail to head like this. If I take that vector and move it up here, then the combination of these two is what I get when I start at the same place and end at the same place. This is my vector here. And I just so happen to pick one where I've got a 30, 40, 50 triangle, right? So this is going to be 50 here. And then what's the angle that's associated with this? I don't know, north, northeast, west, south, east, west, right? I think it's 37 degrees, but the way you would get that is by using this formula here, right? So I take my y component. My y component is my y component is the vertical piece, right? So that's 30. My horizontal is 40. So the angle associated with this is the inverse tangent of y divided by the x, right? 40. So the inverse tangent of 3/4. So I calculate that out, which might be worth doing because you want to make sure that when you do these inverse tangents, you've got your calculator set up. A lot of people have it set on radians. You're going to get different answers, obviously, if you've got it set in radians. But if you've got degrees, you should get an answer that looks a lot like, yep, 36.8698 blah, 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 blah degrees. So just make sure that you can get your calculator to get that answer. If not, talk to me during the break and we'll make sure you can get this right. So what I'm saying here, I guess, the point of what I was getting at is that this equation looks simple, but it's actually hiding a lot of complicated math. And I've chosen actually the simplest possible vector sum I could. In general, this vector sum is actually a geometry problem. And this is kind of in general what it looks like, is that behind every vector sum is a triangle. And that's the main reason that vectors are so powerful, is that we can avoid all the geometry and kind of convert all this geometry into algebra. It's really the purpose of vectors. So you might say to yourself, man, all this vector crap, it's a pain in the butt, right? I'm going to do all this trig and stuff. But if I were to say, okay, forget the vectors, let's talk about the law of cosines and all this kind of stuff. Just imagine doing this geometrically. So that's why we learn vectors. Oh, and I guess the other thing about this slide is that if I'm talking about the sum, the components of the sum are just the sum of the components. That's the really nice thing about these vectors, is that if I talk about C as the combination of A and B put together, well, how far does C go to the right? In this picture, it goes to the right 3 units. Why? because A goes to the right 6 and B comes back 3. Right? So I take the 6 minus the 3, and I get the 3 that's left over. Same thing's happening in the vertical dimension, right? Here, A goes up 2, B goes up 4. So C goes up 2 plus 4 or 6, right? So that's actually the main thing that we're going to be doing over and over and over and over again. You'll do it so many times you'll forget about it. Is that we'll basically we won't ever draw this picture again, right? We'll just say, okay, I got this vector, break it into its components, add the components, and then figure out what the total is going to be. And that's how we avoid all the geometry for this problem.
So would you say that the displacement in the x direction is 3, the total displacement?
Yes, that's exactly what I'm saying. All right. I think I may have had some examples with just vector stuff, so let me double check here. Okay, it was number 6 that I'm going to put in here. If you look at number 6, it says there's a meteor speeding through the atmosphere traveling east. East is to the right, my picture here. It's traveling to the east at 18.3 meters per second. While descending at a rate of 11.5 meters per second. Okay. So it's moving east and down at the same time, right? It's actually moving in this kind of a direction. Okay. So the question is, what is the speed? So I'm being asked for the magnitude of the combination, right? So the magnitude of the combination, the magnitude of this is just going to be given by this formula here, Pythagorean's theorem. Again, this is a simple one because this happens to be a right angle here. Okay, so we're kind of getting lucky on this problem. This is east and this is down. Those have got a 90-degree angle between them. As a consequence, this is just a simple right triangle, which means I can use Pythagorean's theorem. And get the final answer of something, something, something. All right? Which I am just double checking. 21.6. So, that almost was too easy. I should have done a more complicated example maybe. But we'll do some when we get more into the meat of the lecture.
So it's in meter, it's a kilometer.
Sorry?
It's a kilometer.
Oh, you're right. My bad. Kilometers per second is what it says. Because these are the same, they're compatible when I add them, so this is actually kilometers. So I was safe. I really should have converted, but thank you. But the answer is a typo on the answer. I'll fix that later. All right. Okay, I forgot this slide was here. So there's one last thing I want to say about vectors. So the picture on the left here is kind of similar to the one I just showed you, where you've got two vectors being added together, one after the other. And that really happens when we talk about displacement. So if an object moves from here to here, then it moves from here to there, right? Net displacement is just the difference between the starting and the ending point. That's a straight line here. So I call that kind of consecutive addition. But actually, what we'll be doing a lot more frequently is what I'm calling here simultaneous addition. So the reason this is consecutive is because at one moment this happens, at the next moment this happens. I'm really asking about the total time differential, right? So like, for example, when we talk about force, and multiple forces acting on an object, what's the total combined force that's acting on the object? That's a question that's everything's happening at the same moment in time. Also, this example we just went through, when we were talking about velocity, the object is not moving east and then down. It's moving both east and down at the same time, right? So the true trajectory is along this angle, along this descent, right? So this is an example of what I call simultaneous addition, right? Now the truth of the matter is it doesn't matter, because in both cases you can kind of imagine there's this parallelogram that exists with the two vectors I'm adding. It kind of creates a parallelogram, whether I put it on the right side or whether I put it on the left side. It creates essentially the same picture, and the net combination is just the diagonal to that parallelogram. That's why vector addition you'll sometimes see called the parallelogram law, because of this exact picture. But I guess I think it's somewhat important to recognize, at least, that there's a subtle distinction here. So usually in chapter 1, it's introduced as being consecutive, and then we jump into chapter 3s and 4s, and all of a sudden we're doing this simultaneous thing. And I just want to point out here, there's also, and this doesn't matter for you guys, but there is mathematically a distinction between these two that really only becomes relevant when you're dealing with general relativity stuff. So in general relativity, you have to be careful and recognize whether you're doing consecutive or simultaneous addition. But for us, it doesn't matter. And so in this case, the rule is, so I guess I want to say this is basically the rule that we're going to be using going forward, is that we're going to always want to take whichever vectors we're dealing with and collect them together where all their tails are pointing, their tails are all like tied together. So whether the vectors are actually over here, kind of want to mentally bring them together, and that creates the parallelogram that we're creating. So when we do it algebraically, you kind of will lose this picture. You won't have to draw this picture because you're just going to calculate the components, the x and y components. But when you're drawing the picture, and usually when you start solving the problems, you want to start drawing a picture. You kind of want to be careful that you draw it at least reasonably accurate, otherwise it won't really be helpful. It'll be worse than even starting to draw. So anyway, you'll see kind of how this goes going forward. So that is my 15-minute spiel on chapter 1. All right. And like I said in the first lecture, I feel that really this vector stuff is easier to understand as you practice through it rather than me just lecturing on it for the whole lecture. So that's why I combined it. Is that a word? I compound it with chapter 3. All right. So let's talk about chapter 3 proper. As I mentioned earlier, chapter 3 is all about projectile motion. Oh, by the way, the book has got sections 1, 2, 3, 4. We're completely skipping section 4 of chapter 3. We're just doing sections 1 through 3. So sections 1 through 3 in chapter 3 have to deal with projectile motion, and as this slide says, Galileo is really the one who cracked open this problem. So prior to Galileo, there was a long-standing question of what does projectile motion look like when you shoot an arrow through the air. Where does it go? How does it move? And it goes all the way back to Aristotle and before. And so Aristotle had his way of thinking about it. And right around 1200-ish, in the Middle Ages, people were starting to rediscover the Greek writings, picked up Aristotle's works. People were reading that and learning, kind of coming out of the Dark Ages, kind of starting to build universities and things like that, right around the 1200s. And people were reevaluating, rethinking Aristotle's thoughts. Basically like, I don't know about that projectile stuff that Aristotle's got going. And there was basically at the time kind of a general feeling that the basic motion of a projectile, if I launch a cannonball in the air, basically moves at an angle, this initial angle that I start with, right? Basically moves in a straight line until a certain time goes by, and then it kind of stops and basically falls straight down. This was kind of, there are a couple different names that go with this, but there's a guy named Buridan who came up with this idea of impetus. And the idea basically is that when I kick something, when I kickstart something, I invest in it a certain quantity of motion, all right? And that motion carries it forward. And just like a watch that you wind up, as it moves, it basically spends or expels that initial investment of motion, right? And the idea is that after a while, if the more motion I invest into it, the farther it's going to go. But eventually, it winds down, and once it's completed winding down, then it just falls. This is what I call the cartoon trajectory, because that is what happens to every cartoon character that exists, right? Wile E. Coyote is chasing after the Roadrunner, and Wile E. Coyote runs off the cliff. Here's the cliff, right? Runs off the cliff, goes in a straight line, realizes that he has no ground underneath him, and then falls straight down. It's essentially the same idea. So this is kind of really ingrained in kind of the human psyche of how motion goes. The problem is in reality is that motion happens so fast, it's hard for our eye to kind of actually observe what's happening. Now that we've got motion pictures, I think everyone knows that it's not straight. And in fact, even in the Middle Ages, they knew it wasn't really straight. There was some curve associated with it. But what is that shape exactly? And Galileo is the one who figured out it's a perfect parabola. Okay. Now, why is it a parabola? And this was Galileo's great insight into the problem, was that when I talk about this problem, I'm going to break it into its two components. It's got a horizontal motion and it's got a vertical motion. Okay? The horizontal motion is constant velocity. Okay? The vertical motion is constant acceleration. Both of these kinds of problems we now know how to solve, right? If something moves with constant velocity, I'm going to use the equation x equals vt. All right? If an object moves with constant acceleration, then I'm going to use one of the five. I won't write them all up here, but for example, that one, right? And so by breaking the problem into two pieces, and each of those two pieces we know how to solve, we'll be able to make all right, so we are almost to the end of my little deck of slides. The last thing, as I mentioned before we went to break, is that I just wanted to lay out a few formulas that kind of are a shortcut for particular situations. So the idea here is what I've got on the slide. If you've got a problem that involves a projectile that goes from here to the top and then back to where it started, the range associated with that formula or with that motion is given by this formula here, which I'm going to call the range equation. I don't know if it has a formal name or not, but this is quite helpful actually. The range equation would be 0 squared over g sine of 2 times the angle that's associated with the initial launch. Okay, so rather than breaking it into the x and y pieces and doing all that math, this is really just has done all the math for you. It's just that combination of stuff. And so I'll probably walk through the rest of the examples and highlight which ones might be able to allow us to use one of these two equations. Another common thing to be asked in terms of projectiles is how high does it go? Okay? And in that case, the height is given by a very similar looking formula, but notice it's not quite the same. All right? So it still involves kind of the same quantities, the initial velocity, the angle, and the acceleration due to gravity, but just kind of in a different combination. Again, you could actually prove these formulas are true if you just go back to the good old x equals vt, y equals v0 t plus 1/2 a. That form, those two formulas, and combine them together, I guess this would be x. And then the last thing you might be asked is, how long is the projectile in the air? Okay. And that, actually I'm going to change the picture and call that capital T. Capital T is 2v0 over g sine theta. All right. So as I mentioned, I could go ahead and use these and prove these three, but I'm not going to. That will be an exercise for you. Not really. Yeah.
So R is the distance of travels.
R is the total range. So yeah, distance in x that it travels, right? The thing I was thinking about during the break is that the problem we just did actually is one where we could have just used this formula, because that was essentially what we were asked. How long, what's the hang time, was the question for that problem. So if I go back to problem 2 and I look at that and I say, okay, let's try and use this formula, just see what happens. What answer do we get? So the way I do that is I go 2 times the initial velocity, the initial speed, really. The initial speed was 25 divided by 9.8 times the sine of whatever the angle was, 60 degrees. And lo and behold, I just pull my calculator out and do this, right? And see if we get the same answer. Final answer, 4.4184 blah 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 seconds-ish, right? So that looks a lot easier than what we just did, right? 10 minutes ago. So that's obviously the advantage. The disadvantage to these problems is that you can only use them for specific situations, right?
So is the gravity not negative in this case?
G, the letter G is always 9.8 without the negative sign. G is always 9.8. This is, if I want to kind of express the fact that I'm talking about the acceleration due to gravity, I'd probably say something like A is negative G. It's like G represents the magnitude of the acceleration, if you want to think of it that way. And I have to insert the direction with the negative sign. So that's a good call out. In all of these equations, G is just 9.8 without the negative sign. Okay. I'm going to skip 3 for a second. Let's look at number 4 here. So the question is, the ball is thrown upward at an angle of 52 degrees, reaches a maximum height of 7.5 meters. How high would the ball go if it were thrown upward? I want to skip that one. I just want to do a simple one. Let's start with a simple one. Yeah, let's do number 7. All right, so you've got a ski jump essentially here. ski jump launches the skiers at 63 degrees. Should have wrote those in a more convenient spot. So you've got a ski jump here, and right at this point here, that's a 63 degree angle. Okay? So it says the skier attains a height of 13 meters above the end of the ramp. So that means the skier actually is going to move on a projectile like this. This height here is what I'm being told. This height is 13 meters. So what's the skier's launch speed? So the question is, what is the initial speed here, right? And the reason I picked this is because this formula contains all those quantities, right? So basically, I'm told the height, I'm looking for the initial velocity, I know this is 9.8, and I'm given the angle. So I should just be able to plug all this into the formula and go. So in this case, at 13 equals v0 squared to 9.8. So if I do a little bit of math here, I'm going to simplify all this stuff here. So 60, so sine of 63 squared, divide by 2, divide by 9.8. Get this all equals basically 0.04, 0.0504, blah, blah, blah. V0 squared. Pull this over. Divide both sides by that number. I get 320.95 equals V0 squared. V0 is square root of that. .91 or 18 meters per second using two significant digits, right? So that is an example of using the shortcut formulas. Yay! But not in every case can you use the shortcut formulas. Dang it! Let's look at number 3. Let me erase everything. Okay, problem number 3. So you've got an airplane. It's actually flying at an angle downward, right? 30 degrees from the horizontal. It's flying downward. And it drops, what does it drop? A flare, all right? It drops a flare when it's 2.4 kilometers above the ground. So, eventually it follows its normal parabolic shape, right? It's not really at the top of the parabola. It's hard to draw mathematically what this parabola would look like. It would keep going up and kind of look like this, right? So this isn't the top of the parabola, it's kind of at an angle, right? It's a tangent. And then, but eventually it falls and hits the ground. So the question is, what is this angle here if I were to just draw this geometric triangle, right? Remember, the path of the flare is along the blue dashed curvy line, not the straight hypotenuse that's drawn on the diagram. But we need the diagram, or we need the hypotenuse in order to define what we mean by that angle, right? So, if I look at that diagram and I say, okay, what I see is a right triangle here. Okay. So I've got one of the sides of that right triangle. I'm looking for the angle inside the triangle. If I only knew one of the other sides, I would be golden, right? Because this is the opposite side. So opposite hypotenuse, I would use the sine. Opposite and adjacent, I would use the tangent. So the question is, which one of these am I going to be able to get? And the answer is this distance is going to be easiest, because in almost every case, I'm going to break the problem into its horizontal and vertical components anyway. And so in the process of doing that, I'm basically going to figure out what this x distance is. And so it's kind of leads me to believe that this x distance is what I'm going to need in order to solve this, which means I'm going to use tangent at the end. So let's talk a little bit about this x. Is there a way for us to figure out what that x is? Well, first thing I do is I check all my shortcut formulas. Shortcut formulas are designed for this kind of football type problem. This is not a football type problem. So it means I got to fall back on first principles. First principles say take the motion and break it into its x and its y pieces. So that's what I do. I say, okay, I've got the horizontal motion and I've got the vertical motion. Right? The horizontal, I'm going to use v equals xt. The vertical, I'm going to use this formula or a variation on it, right? Okay, so what do we know? In the x direction, we do know the speed, the initial speed of the projectile, the flare, right? We know the speed of the airplane, and although it doesn't explicitly say the flare is released from rest, we can assume that, I guess. Flare is not a rocket, so it's basically just released by the plane, which means when it's released, it's moving along with the plane. It shares this initial velocity, right? So this is the initial velocity of the flare as well. The direction is also shared by the flare, so both of these, even though we're talking about the airplane, we'll assume it's true of the flare as well. So that means I got a speed and direction of the speed, which means I can get the initial velocity. So that's good. And actually I know x is what I'm looking for, right, to finish the problem off. So this is looking good. X is what I want to figure out. The x component of that speed, well, this is where I would draw a little diagram. And here basically the initial speed is, 240? For a second. The angle here, and this is where it kind of gets a little bit tricky. What picture is showing me this is 30 degrees, right? I've kind of messed things up. Let me clean up my picture a little bit. So if this is the angle I'm given, here's the geometry trick I mentioned in the first lecture that we're going to do again and again and again, is that when you've got two lines that cross each other, the angles on opposite sides of the intersection are equal to one another. So this 30 is the same as this 30. The reason that's important is because this Vx is what I'm looking for, and that means I know that the angle inside there has to be the 30 degrees. Make sense? I mean, when you draw a picture, it looks really clear that these two angles are the same. Maybe I've done such a bad job of drawing this that you can't tell. This is the initial speed. What I want is the x component of that speed, right? Which means I'm going to draw this right triangle. This is the y component of the speed. What I'm saying is that has to be 30 because they're opposite of the intersection. So if this is the angle that I'm given, this is opposite or adjacent?
Adjacent.
It's adjacent to the angle. So adjacent means I'm going to use sine or cosine. I'm going to use cosine. So this means, oh, sorry. Right. And I'll just do the math. All right, so if I knew t, I'd be done. But I know nothing about the time. All right, fine. So let's talk about the vertical. We've left off this whole piece of the puzzle, right? What do we know about the vertical? We always know a is negative 9.8. Actually, I know the height here. What's this y? Sorry? Yes? Looking for something else. Negative. Negative 2.4. Negative 2.4 because it falls downward. All right. And then the initial speed in the y direction actually is given by this same argument over here, but instead of cosine, I'm going to be using the sine. This is what goes over here. So I've got the sine 30 degrees. So I've got 240. I think that one's just the 120. Let me check. And that's great. I've got 3 quantities. I need 4 quantities. The 4th is my unknown, but what am I looking for? Well, it's either t or the final velocity. T sounds somewhat suspiciously familiar, right? I want to know t because the t here is the same as the t here, right? The time it takes to fall is the same amount of time it takes to move to the right. So I can use this right side to calculate the time involved in the fall, use that time to figure out how far it gets displaced to the right, and that is going to get me to finish off this triangle. So looking at these quantities, I am going to use my good old friend y equals b0t plus 1/2 at squared. Negative 2.4. Something like that, right? Now I look at that and I go, oh my word, that really is a quadratic equation, right? No way around it. Son of a gun. Okay, how do I do quadratic? Yeah.
Just real quick, will y be negative 2400?
Yes, excellent. I was going to mention that, but I'm glad you saw it. This Vy is pointing down, right? So because that's pointing down, this Vy should be negative, right? So this actually is not 120, it's negative 120, right? And so really, how do I kind of keep track of the bookkeeping here? I think the easiest thing is to just put it right at the beginning of this formula. Go ahead.
The question was for y, the negative 2.4.
Yeah?
It's negative 2.4 kilometers, which should be
Oh,
2400 meters.
I misunderstood you. Okay, yes. So it's not 240, but 2,400, right? When you said 240, I thought you were talking about this 240. But still, it gives me an excuse to talk about the fact that this velocity is actually pointing down. So because that's pointing down, I need to make sure that I put that sign in here as well. So that means that really my quadratic equation looks like this, and then this, I'll correct this now. And that's the correct formula, right? Did I make any other mistakes? Very possible. Good. All right, so the way to do this, quadratic equation, everyone remembers and loves the good old quadratic equation, right? Yes? Yes. Yes, I love the quadratic equation. Alright, so in order to use the quadratic equation, I need to get this in kind of standard form, which is ax squared plus bx plus c equals 0. So I need to rearrange this so it looks like that. And so basically I gotta get everything on one side. The easiest way is to add this 240 to both sides. So I'm gonna get, this is negative 4.9 t squared minus 120t plus 2400 equals 0. Right? So now that I've got it kind of in standard form, I've got t equals negative b plus minus square root b squared minus 4ac all over 2a. Everyone's got that memorized, right? You don't have to memorize it. So I do that. This is already negative, so I mean this is my b, this is my a, and this is my c. 120 plus minus square root 120 squared minus 4 a c divided by 2 a blah 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 blah. Right? And then you just do this. And look at that, I already did it, man. I'm not going to do it again. Alright? So the answer, when we're done with all this, we get t is one of two numbers. It's either 13.048 or it's negative 36.206. Which do you think? Negative.
Go back in time.
No, we don't go back in time. What do you think this is? Back to the future? So this is the time I'm going to be involved in. This does mean something, but it's not relevant to our problem. So if that's the time that it takes for the flare to fall from the plane to the ground, it's also the time it takes for the flare to move its horizontal distance, which means that that t is what goes here, which is what I'm going to plug in here. So finally, the x displacement is 207.34 times this last. And I'll just do this in my head real quick. 27120. That is the total distance in the x direction. So if this is 2.712 kilometers and this is 2.4 kilometers, then this angle here is the y over the x. And this is just an exercise in calculator gymnastics. So I'll let you do it on your own time. 41 degrees. 41, what's the answer? 41.5. Final answer. So I know that there was some kind of distracting math, I guess, using the quadratic equation and kind of this weird end game on the problem. But the basic principles are still here, where you take the motion, split it into two pieces, and then go. All right, so I think that's the last kind of complicated one. Let's do a couple of easy ones. Let's do number 4. Let's just go down one by one. Number 4, a ball is thrown upward at a speed of blah, a speed of beep, an angle 52 degrees above the horizontal, reaches maximum height 7.5 meters, blah, 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 blah. So the first step for me is to extract all the data. That's step number 1. But step number 0 is to draw a pretty picture. So we draw our pretty picture. Degrees. V0 is actually what I'm looking for. This is the initial speed. I know that it's going to be kind of a parabola shape. What I'm told is this height. This height is 7.5 meters. And I look at that and I say, oh yes, this is one of my shortcut formulas. So let me kind of pull that back up. The height of this kind of a shape is given by the formula v0 squared over 2g sine squared theta. All right, so let's put all this stuff into the formula, see if we can figure something out here. 7.5 on the left, v0 squared is what I'm looking for, 2 times 9.8 sine squared, 52 degrees. Looks pretty good. I should be able to solve for that v0. v0 equals oh boy, what the heck? Want me to do that in one shot? Do everything right. I get syntax error. That's great. Good to know. Final answer, 15.386 meters per second. Okay. Don't forget to do the square root at the end there. So that's the initial velocity. Awesome. All right. Oh, that wasn't actually what I was asked. Dang it. Why don't I read the problem? So the question is, how high would this same ball go if it were thrown straight up at this speed? Okay, so what you're saying is, basically now I have a different situation where I'm going to have the ball and now I'm just going to launch it straight up, kind of like the web. The question is, how high up is it going to get now? Well, actually, it's still kind of the same problem, right? In fact, I can still use this exact same equation. But in this case, the height, but in this case, the angle is this angle here, right? That angle is 90 degrees. But I can still use it because it's just a normal projectile problem. So in this case, I know what v0 is. It's my answer from the first part. Squared divided by 2 divided by 9.8. Right. So I just use the same equation for the different situation and calculate. What's the sine of 90 degrees? 1. Very good. So I did everything right. My final answer here is 12.078 meters. Yeah.
So why 9.8 is not negative?
Because the letter G is the magnitude of the acceleration due to gravity. So G is 9.8. It's what G means. It's the definition of G.
So when is negative? So
Why is it?
when it is, we calculate as negative.
Well, short answer is G is never negative. It's never negative. G is never negative. The acceleration due to gravity is always negative. So I'm saying that very specifically. I'm being very careful with my words. So you got to hear the distinction what I just said. The acceleration due to gravity is negative 9.8. The magnitude of the acceleration due to gravity is negative 9 is 9.8, right? So notice when I write it this way, I use the letter G. When I write it this way, I use the letter A. Never do I write G equals negative 9.8. I never write this. So I'm always writing A is negative 9.8, but G is 9.8. In other words, I could write A is negative G. It's kind of the shortest way to kind of express the distinction I'm trying to
So
say.
it is depending on which one we have in the formula, right? If we have A, we have to use negative 9.8. If we have G, we have to use 9.8.
Yes, that's another way to think it. Yep. And so you'll notice in all these equations, these shortcut equations, it's always G.
Okay.
Thank you for asking, because I know that's confusing. So, all right. Okay, so with that. All right, let's look at 5. Just go one by one. Man, we are like powerful now in this class. Just throw at problems at me, man. I've got all the tools in my toolbox. Good to go. Oh, until I get one I can figure out. All right, so let's look at number 5. Number 5 says you got a fire hose, you're a fireman, stream of water flying at an angle of 35 degrees above the horizontal. Water leaves at 25 meters per second. So again, step 0 is to draw my problem. So you always start with the fire hydrant in this case, right? Fire hydrant. Here's the hose. Here's the water. So the problem's even nice enough to say explicitly the water moves like a parabola. This angle